Welcome to Section 6, Lesson 6. In the previous 5 lessons, we covered linear systems of two equations in two variables and the algebraic methods for solving them. Today, we extend the same toolkit to 3 equations in 3 variables. The geometric picture changes from 2 lines on a flat plane to 3 planes in 3-dimensional space, with the unique solution being the single point where all 3 planes intersect. The algebraic strategy is straightforward. Use elimination twice to reduce the 3-variable system to a 2-variable system. Solve that smaller system using the methods from the previous lessons and back substitute to find the 3rd variable. Today we lock in the 4-step procedure and walk through one clean example illustrating the workflow. First idea on the board. A 3-variable linear system has the form 3 equations like a x plus by plus cz equals d, with each equation having its own coefficients on x, y, and z and its own right side constant. The unknowns are x, y, and z, and the solution is a triple of values that makes all 3 equations true simultaneously. Geometrically, each equation describes a plane in 3-dimensional space, and the solution to the system is the single point where all 3 planes intersect. For most well-posed 3-variable systems, this point exists and is unique. Second idea, the strategy is to use elimination twice to reduce the 3-variable system to a 2-variable system. Step 1, choose which variable to eliminate, say z, and pick 2 equations to combine for the elimination. Combine those 2 equations to produce a new equation in just x and y. Step 2, pick a different pair of equations from the original 3 and eliminate the same variable z from that pair, producing another new equation in just x and y. Now we have 2 equations in x and y, a standard 2-variable system that we already know how to solve. Third idea. Step 3, solve the 2-variable system using substitution or elimination as appropriate. Step 4, back substitute the solved values of x and y into any of the original 3 equations to find z. Verify all 3 values in all 3 original equations as a final check. The procedure scales to 4-variable systems, 5-variable systems, and beyond by repeated elimination, with each elimination step reducing the variable count by 1 until we reach a 1-variable equation. Today's worked example walks through the procedure on a 3-variable system at the standard textbook level. A 3-variable linear system has 3 equations in 3 unknowns x, y, and z, each equation describing a plane in 3-dimensional space. The solution to the system is a triple of values that makes all 3 equations true simultaneously, geometrically the unique point where all 3 planes intersect. Here is the 4-step solving strategy. Step 1 is to choose a variable to eliminate first. Look at the 3 equations and decide which variable has the cleanest coefficient pattern across the equations for cancellation. Pick 2 of the 3 equations and use elimination to cancel the chosen variable, producing a new equation in the remaining 2 variables. Step 2 is to repeat the elimination on a different pair of equations. Pick the 3rd original equation paired with one of the 2 used in step 1 and again eliminate the same variable. The result is a second new equation in the remaining 2 variables. The 2 new equations together form a 2-variable system that the Section 6 methods can solve directly. Step 3 is to solve the 2-variable system using substitution or elimination as appropriate. Apply the decision rule from Lesson 4 to choose the better method. The solved values are 2 of the 3 original variables, leaving 1 still to find. Step 4 is to back substitute the 2 solved values into any of the original 3 equations to find the 3rd variable. The choice of which original equation to back substitute into does not affect the answer. Pick the one with the cleanest arithmetic. Verify the full triple by substituting all 3 values into all 3 original equations. 3 matches confirms the solution. The procedure produces exact answers for any well-posed 3-variable system and scales to larger systems by repeated elimination. Here is the worked example. Solve the three-variable system. Equation 1 is x plus y plus z equals 6. Equation 2 is 2x minus y plus z equals 3. Equation 3 is x plus 2y minus z equals 2. Use the four-step elimination strategy. Step 1. Choose a variable to eliminate first and pick two equations. Eliminate z by adding equation 1 and equation 3. Their z coefficients are plus 1 and minus 1, exactly opposite. Add equation 1 plus equation 3 gives 2x plus 3y plus 0z equals 8. Call this combined equation A. 2x plus 3y equals 8. Step 2. Repeat the elimination on a different pair, still eliminating z. Use equation 2 and equation 3. Equation 2 has z coefficient plus 1 and equation 3 has z coefficient minus 1, again opposite. Add equation 2 and equation 3, 3x plus y plus 0z equals 5. Call this combined equation B. 3x plus y equals 5. Step 3. Solve the two-variable system A and B. Equation A. 2x plus 3y equals 8. Equation B. Z. 3x plus y equals 5. Use elimination to cancel y by multiplying equation B by 3. 9x plus 3y equals 15. Subtract equation A from this. 9x plus 3y minus the quantity 2x plus 3y equals 15 minus 8, giving 7x equals 7. So x equals 1. Back substitute x equals 1 into equation B. 3 times 1 plus y equals 5, giving y equals 2. So x equals 1 and y equals 2 are two of the three solution values. Step 5. Plug x equals 1 and y equals 2 into any original equation. Use equation 1, 1 plus 2 plus z equals 6, giving z equals 3. So z equals 3. Step 6. Verify. Equation 1, 1 plus 2 plus 3 equals 6. Match. Equation 2 times 1 minus 2 plus 3 equals 2 minus 2 plus 3 equals 3. Match. Equation 3, 1 plus 2 times 2 minus 3 equals 1 plus 4 minus 3 equals 2. Match. All three equations satisfied. So the solution is x equals 1, y equals 2, and z equals 3. The big lesson from this example is the cancel, solve workflow. Two elimination steps reduce the three-variable system to a two-variable system. The section 6 methods solve the smaller system, and back substitution finds the third variable. The strategy is mechanical. Once practiced, scales to larger systems through repeated elimination, and is the manual algorithm that underpins Gaussian elimination in linear algebra. Three-variable systems appear constantly in real-world problems with three balanced quantities, three competing constraints, or three unknown parameters in a three-equation model. Here is a second worked example to lock in the procedure on a slightly different system. Solve equation 1 is x plus y plus z equals 9. Equation 2 is x plus 2y plus 3z equals 14. Equation 3 is 2x plus y plus z equals 10. Step 1. Eliminate x first. Use equations 1 and 3. Subtract equation 1 from equation 3. 2x plus y plus z minus the quantity x plus y plus z equals 10 minus 9, giving x equals 1. Step 2. Wait, that elimination produced an immediate solution for x. Sometimes the structure of the equations gives a free variable solution at step 1. We have x equals 1 already. Now substitute x equals 1 into equations 1 and 2 to get a two-variable system in y and z. Equation 1 becomes 1 plus y plus z equals 9, so y plus z equals 8. Equation 2 becomes 1 plus 2y plus 3z equals 14, so 2y plus 3z equals 13. Step 3. Solve the two-variable system. From the first reduced equation, y equals 8 minus z. Substitute into the second 2 times the quantity 8 minus z plus 3z equals 13. Distribute as 16 minus 2z plus 3z equals 13. Combine 16 plus z equals 13, so z equals minus 3. Step 4. Back substitute z equals minus 3 into y plus z equals 8, y plus negative 3 equals 8, so y equals 11. Verify the triple x equals 1, y equals 11, z equals minus 3 in all three original equations. Equation 1, 1 plus 11 plus negative 3 equals 9. Match. Equation 2, 1 plus 2 times 11 plus 3 times negative 3 equals 1 plus 22 minus 9 equals 14. Match. Equation 3, 2 times 1 plus 11 plus negative 3 equals 2 plus 11 minus 3 equals 10. Match. All verified. So the solution is x equals 1, y equals 11, z equals negative 3. The big lesson from this example is that the elimination strategy sometimes produces a free variable solution early when the equations have favorable structure. Subtracting two equations that differ only in one variable gives that variable's value directly. Recognizing the structural shortcut on every system saves time, but the general four-step procedure works regardless of whether such shortcuts exist. Practice both patterns to develop the workflow flexibility needed for harder systems and for harder math classes that build on this material. 3 mistakes that catch every algebra student during their first weeks of 3-variable system work. Each one is fixable with a small explicit habit applied on every problem. First mistake: trying to eliminate a variable from a pair of equations whose coefficients on that variable do not align directly. A student wants to eliminate z from equations 1 and 2, but z has coefficient plus 1 in equation 1 and plus 3 in equation 2. Direct subtraction does not eliminate z. Multiplication by 3 on equation 1 is needed first to align the coefficients. The fix is to scan the coefficients across all 3 equations before choosing the elimination pair, and to pick a pair whose coefficients are equal or opposite directly when possible, or that align easily through small multiplications. Second mistake: solving the reduced 2-variable system and stopping without finding the third variable. A student executes steps 1 through 3 cleanly, gets x equals 1 and y equals 2 from the 2-variable system, and declares those as the answer. The system has 3 variables, so the solution requires 3 values, including z. The fix is to remember the back substitution step 5 explicitly, plug x and y into any original equation to find z, then state all 3 values together as the complete solution. Third mistake: verifying the solution in only 1 or 2 of the 3 original equations rather than all 3. A student substitutes the solution into equations 1 and 2, finds both match, and skips the verification in equation 3. If the system has a subtle algebraic error in step 1 or 2, equation 3 can fail silently while 1 and 2 pass. The fix is to always verify in all 3 original equations as the final step. 3 matches gives high confidence, a single failure flags an error that needs revisiting. 3-variable systems appear constantly in 3-dimensional physics, chemistry, stoichiometry, color analysis, and any modeling problem with 3 balanced quantities. 4 broad sectors below. In physics, the equilibrium of a 3-dimensional rigid body under multiple forces produces a system of 3 equations expressing that the net force in each spatial direction x, y, and z is 0. Each force component contributes to the corresponding equation, and the system of 3 equations in the unknown forces or accelerations is solved using exactly the cancel-solve workflow from today. 3-dimensional statics analysis of structures, vehicles, and mechanical systems all rely on 3-variable systems. In chemistry, balancing a chemical reaction equation produces a linear system in the unknown stoichiometric coefficients of the reactants and products. For a reaction with 3 or 4 compounds, the conservation of each element produces one equation, giving a small linear system that elimination solves cleanly. Chemistry teachers and students use this technique on every reaction balancing exercise, often without recognizing that the underlying mathematics is exactly the 3-variable system algebra from today. In color analysis and computer graphics, matching a target color from 3 primary colors red, green, and blue produces a 3-variable system in the unknown intensities of each primary. The conservation of total brightness and the matching of 2 color channels gives 3 equations, and the solution is the RGB triple that produces the target color. Color management software and image processing libraries solve such systems continuously when converting between color spaces. In linear algebra, Gaussian elimination is the algorithmic generalization of the cancel-solve workflow you learned today, scaled to systems with many variables and many equations. The matrix of coefficients is reduced through systematic row operations to upper triangular form, then back substituted from bottom to top to recover all the variable values. The textbook method scales the manual procedure you learned today to systems with hundreds or thousands of variables executed by computer software in scientific computing, machine learning, and many other professional contexts. 3 things to take with you from this lesson today. 3 variable systems are the natural extension of the 2 variable systems from earlier in this section, and they are the gateway to all of linear algebra and to scientific computing techniques used across the entire field of applied mathematics in higher math classes you may take in college and beyond. First, a 3-variable linear system has 3 equations in 3 unknowns, with the solution being a single triple of values that makes all 3 equations true simultaneously at the same time. Geometrically, each equation describes a plane in 3-dimensional space, and the solution is the single point where all 3 planes intersect. For most well-posed systems, this point exists and is unique. Second, the 4-step solving strategy is cancel, solve, back, substitute. Use elimination on 2 different pairs of the 3 original equations to cancel the same variable in both pairs, producing 2 new equations in the remaining 2 variables. Solve the resulting 2-variable system using the methods from earlier in this section. Back substitute the 2 solved values into any of the original 3 equations to find the 3rd variable. The 4-step strategy is mechanical once practiced and scales naturally to larger systems through repeated elimination. Third, always verify the full solution triple in ALL3 of the original equations as a final check before declaring the answer. Verifying in only 1 or 2 of the equations can miss a silent algebraic error in the 3rd equation. 3 matches confirms the solution. A single failure flags an error that needs revisiting. The verification step is fast and is the cheapest insurance against silent errors in the elimination chain. Coming up next, the lesson called Word Problems with Systems, where we apply the system solving toolkit to real-world translated problems where 2 or 3 quantities need to be solved for simultaneously. Word problems are the main practical use of system solving across science, engineering, finance, and business, and the system algebra you have built across this section provides the mechanical tools for those applications.